Hello! In some of my other videos, not many, you might have seen me using this. This is a very basic oscilloscope which was built from a kit, and it was more about could I actually solder some of the little tiny surface mount parts to see if I can get it right. And the answer is at first no, but fortunately it came with a very good set of instructions to say if it doesn't work, measure voltage between here and here, and depending what you get you can sort it out. And after the 3 effective fixes it was good. But it was a bit noisy. But at the time it was so cheap, it's like 20 something pounds. I thought that would be the only real way that I could afford an oscilloscope ever. But things have changed and oscilloscopes are cheaper and you don't have to make them yourself anymore. So I've got one here. This is called the DSO-TC3. It is a little scope and it does things as well like test some components out to see if they're working, and it works as a signal generator. We get this and we get this bag with some bits in it, and we'll go take a look and see what's there in close-up. Just beforehand, I have to say I'm not that hot on electronics. You know, I know how to put wires together and what the basic things do, but I don't know an awful lot about them. I sort of understand signals from a sort of basic standpoint about like how PWM works and how PPM works and what I'd sort of see from servo stuff. But I thought it was a way of being able to find out more about it, and I thought this might work as a diagnostic tool for those of you that are messing about with things and wanting to know what's going on. So I thought, well, let's unpack it, see what there is, and let's see what we can measure and see what we can understand from it. So let's go. Okay, let's get out of the box and see what it comes with. This little box here, come to that in a second. We've got some instructions here. Fairly thick manual, but there's lots of different languages, so you can tell a bit of a warning function about how to use it, which I will have to read because, as I said, I really don't know much about the right way to use the oscilloscope. I've kind of been faking it all this time and seeing what I can work out. And here's the little unit itself, and we can turn it straight on. It's got quite a nice colour display, and we got this test thing here. The scope itself, a signal generator, so you can pass a signal through to something else. Tools. This tester, apparently you put things in there and then this goes down and they sort of close and hold that. But we'll come to that in a second. Let's just find out what's in here. Okay, so we've got a USB lead and we've got USB here. I presume that's for charging. It might be the fact that it's got updates you can do as well. I just noticed a little stand at the back there. Up the top here we've got various connectors. I don't know what the difference between DSO DDS is. I guess that's the live. I really am flailing a bit here, but we've got some bits and bobs here. Let me just get these out. So we've got this thing which I guess plugs into one of these, and we put it on a ground connection and the thing we're measuring. We've also got these things. These are pretty cool, so we can clamp hold on those, and then we've got these little things, and we can basically push that up and that little sort of hook comes over, and then we can let it go and it sort of grabs hold of a wire. That's the idea of those. And then, as I said, we've got this other bag here, and in this bag we've got a sort of BNC style connector, another ground thing, and another little thing to hook onto. Quite what the difference is between this and the other one we'll find out. It's got this little thing there that says 1 times, 10 times, and I don't quite know how it works. Obviously that doesn't plug in directly, so we've got this secondary bag here, and in this we've got this little whatever that connector is that goes in there to BNC converter, and we've got some other little plastic rings which I don't quite understand what it's for. I sound like a real expert, don't I? Yeah, I'm starting kind of from scratch here. I think the most important thing to know about oscilloscopes is that the base function is that they measure voltage over time, and those little squares will scale in at this point 100 millivolts, and each of the squares going along is 200 USECs. So it will effectively put a voltage over time, but the difference is here we can freeze that time, we can set trigger points so it will sort of hold it and very accurately show us what's going on. And of course, because it's so accurate and because we can show those signals over time, we can basically investigate really minute signals in tiny timestamps, which is kind of interesting to me. I'm going to read the manual, find out kind of how to do it, take the screen protector off, and yeah, then we're going to try and have a play of it, see what it can do, see what some of the other functions are. Okay, so it turns out this is to help you measure large voltage. It's got this 110 time 10s thing here, and it goes in collaboration with that. So usually you can put up to 40 volts in. If you change this to 10 times and change this little one here from 1 times to 10 times, you can go up to 400 volts. I'm not going to be doing that, so I'm not particularly worrying about it. But the first thing I thought I'd attempt to show you is a PWM output, which a servo would make. What I've got here is a little servo tester, and that's going to put a PWM signal out. So if we plug this in, so this is what a PWM output looks like. Basically it's got this thing where the signal goes high, which varies depending on the servo position you want, or position on the channel you want. And if I change this down to 500 milliseconds, you can count each one of these. So at the minimum position it's at about 1000, its maximum position's about 2000, and the in-between is about 1500, which you should recognize the USEC things if you've ever used Betaflight and you're trying to sub-trim everything just perfectly so your channels are right. And the way a servo works is it expects this signal every 20 milliseconds, and if we change this to 20 milliseconds, you should see that every little square we've got our signal there. This isn't actually static. What is happening is we've got this trigger point here, and it basically says when the signal hits that height, stop it. And what it's doing is basically stopping every one of these. So in effect it looks like it's static, but it's actually moving along really quickly. And we can change that. If we go like this and we move it, we can see that each of these signals every 20 millisecond is generating a slightly different wave as we move this along here. That's the servo on a sort of test mode. So you can see it just doing the 2 positions there as it goes, which I find fascinating. It's a real help for me to actually look at these and see them and figure out, oh, that's what it looks like. And this is very much an analog signal. This is just like signal goes high for a certain amount of USECs, and then we have a gap for up to 20 milliseconds before the next signal comes along, and any changes there can be interpreted. But it's great at this because there's like, oh okay, there's a very obvious like bit here, and then we hit it as it goes up. This little symbol here means it's trying to trigger as it rises. We can actually change that down the other way. If we do this, this is the trigger as it descends. So obviously it makes more sense to do it there. But if we've got a more complicated signal, like PPM, this is where it becomes more difficult. So PPM is effectively PWM, but all the channels strung together, and then there's a larger gap here in between the two, well, the next signal along. So let's see if we can capture that now. So what I'm doing right here is I'm clamping on to a little audio cable, and that is out of the trainer cable of this radio I just reviewed, the Radio Master MT. And there's a slight problem with this in trying to capture it. The first thing you'll notice about it, and what I can do, I can just get rid of this text here, although you will notice that one of the problems it's having is its cycle is kind of all over the place. It doesn't know quite what the signal is. So if I do this, that gets rid of that information. And what we can then do is, if we say single, that is a single capture. And from there you can see the 1, 2, 3, 4, 5, 6, 7, 8. Looks like 8-ish channels on there at the moment. So if we say auto again, it keeps going. The other thing you might notice is A, it can't decide where to stop, and B, it's inverted. So the signal is high and then goes low for each of the channels. But the only pain is it's a bit hard to see. So let's see if we can expand this a bit. If we put this on the 2 milliseconds, and let's see if I can just capture one of these, you can actually see the individual channels there, and then you've got this gap for PPM, which is like, that is the end of all my information. It has a certain PPM gap, and then it starts again over here. So the thing we can't do with this is accurately get it to hold on that gap, and no matter what I do in terms of whether it's like 5 milliseconds or 10 milliseconds or whatever, or going much lower where I can only see part of it, it's not good at stopping in the right place. More expensive scopes have this thing called a pulse width trigger, and what you can do, you can say if the pulse goes high for X amount of time, and you'll see we've got an X amount of time here, we could say trigger there, and then we'd always get this nice solid set of info available, so we can always literally move our sticks and we can see it looking like it's static. So that's a bit of a shame, that one, because these are sort of the signals I really wanted to look at. But let's try something else. Let's try something more digital. If we have a look at an SBUS signal, that should be very much a sort of packet, ones and zeros, but we should still be able to see that, because ones and zeros of course will basically pulse up and down, and you can basically decode binary if you've got a high resolution enough look at that, because it will either go high or low for 1 or a 0 and go along, and you can decode the packet that way. Probably not on this, but let's have a look at it anyway. Okay, what I've got here is this L9R plugged into SBUS, and you can see we've got basically this big data packet here, then a gap, then another big data packet, which is about as well as I can see it. Now what happens if I was to go, you can see the packet's pretty well there, but if I was to go downwards and try and actually see what that data looked like, it's a bit tricky. So if we go down to as little as, I don't know, say 20 USECs, and we do a single, what we've got here is basically bits of a packet. Essentially, depending which way it's round, I can't remember if this is inverted or not, that's like zeros, up there is ones, and if you had the right sort of scope that could hold this and you could scroll through them, you could pretty much work out the actual packet decode. Of course, this would be much easier to do with something like an Arduino, where you can actually do the right sort of timings to read this properly. But it's kind of interesting to see it on a scope, because you kind of think of digital as not being a thing you can look at, but you absolutely can look at it. It's just a case of like the signal is kind of the same, it's either up or down, but each of these little up or downs represents like a single bit. So that's probably a 1 or a 0, that's the opposite, and it carries on that way. Again, if we could trigger on a pulse width, we'd have a much better chance of seeing them, but them's the breaks. You can actually see there's a hell of a lot of data in an SBUS packet, because it's not simply like we have a little gap every time for the channel. On each of the channels we have I think it's like a 13 byte information about stuff, so the whole packet is quite a lot, and you can see there's much more going on than just a simple PWM signal. And it'd be the same if you looked at CRSF or something like that. I don't know the packet structure of that one, but it's going to use digital information to do it. So I find this a really useful way of learning about things, and to a certain extent debugging them, but not to this sort of level, because it's very hard to like hold it and examine it in any detail. So that's a little bit about the oscilloscope. The other thing we've got here is this thing called M-Tester, and if we go into that, it basically says put unknown or damaged part into this bit, And I felt this was quite interesting because sometimes, you know, there's stuff we want to test out. So I've got this 1000 microfarad capacitor here, and it's like, well, how do you know if a capacitor's working or not? How do I test out if a capacitor's good? And I've just put that in, and I put this down to make sure it's okay. Press OK, it's testing, and tells me it's a capacitor. It thinks it's 1074 microfarads, which is pretty good, and tells you your VLOS and your ESR, none of which I know what mean, but you've got those in case you want it. And then we've got things like, here is a resistor. I've no idea what this is. I suppose I could test it with a multimeter, but I never learnt what the bars mean in terms of decoding it. So let's see what this says. It's a resistor. 20.28k ohms. Pretty cool. Found this little thing as well. It just says 1N0K100. No idea what that is. It's a little capacitor. And I think this is a diode. But like I said, I'm not so good at my electronics. It is a diode. I'm trying to get better, but there's quite a lot of reading to do. And this one should be some type of transistor, which I don't know about. And there it is, transistor NPN, which is about how the trigger works or something. Again, I'm kind of new to transistors, but I wanted to know about them because essentially that's what FETs and MOSFETs are in a different kind of way. And I just don't know what they are. Anyway, pretty useful. I'm sure there's a lot of this you can do with a multimeter, but I find it quite handy. And I've got a lot of very classic consoles, and doing things like being able to test out if things need recapping and stuff seem pretty useful to me. There's a whole bunch of toolbox stuff about like measuring voltage and different things. There's an IR decode thing. Get a remote like this, start pressing the buttons, and you get off screen. Just press some of the buttons. And I don't quite know where this comes in handy. I guess if you're programming something and you need to know stuff about the IR codes generally, it's quite handy. I won't go through all of these, but you get the gist. Mostly because I don't know what these ones are. They're different types of tests. Voltage wise, like I said, I'd use a multimeter. This is where these things come in. You've got, this is for measuring voltage, this is for doing the signal generation out, and this is coming in for the oscilloscope. So I guess that leads us on to signal generator, which I'm not quite clear where you'd use it for. I've watched a couple of people review oscilloscopes, and the first thing they do is put a pulse generator on to show whether it can do it or not, which seems a bit odd. I would have thought, you know, there's other things you could measure, but I suppose we should try it, shouldn't we? So the only way of really doing this is getting my old scope out and doing it again, and this is the problem with my old scope. You can see the noise on the screen there, but this is a sine wave, and we can change the frequency. 1, 30. Ooh, 4, wow, it moves quickly. So it suddenly went from 100 Hertz to 40,000. It's 400 Hertz. So that's a square wave. And we can change the timing on this end as well. See a bit more. An awful lot of difference between a square wave and a pulse. Triangle. A ramp. Same sort of thing. And that's just DC at 3 volts. Yeah, well, it works. I've just no idea what you're supposed to use them for, which is my problem. Unfortunately, what I can't do is generate signals here to see how they display here, which I'm thinking would be a lot better. But that's not too bad. That's fairly clean on that one, finally. So yeah, it seems to work. What's it for? Don't know. Now, usually when I review something, I like to have a bit of knowledge about what I'm doing, because otherwise I can't speak from any sort of experienced position to say this is good, this is bad. This is more of a thing where I'm completely clueless really about how oscilloscopes work other than the very basics. But this is more of a case of like, I couldn't afford a great big impressive one, but this seemed cheap enough to be worthwhile to experiment with. And basically I like learning about stuff, and I'd like to know more. I've got some sort of real world things to do with this. This, if you recognise this, is a PlayStation interface. This is from a project called Blue Retro, and the idea of this, it uses an ESP32 chip with Bluetooth and Wi-Fi enabled. You plug it in, it powers it, and you can connect a wireless Bluetooth joystick, like a PS4 remote in my case. This isn't working. I've actually replaced it with another one, and that's fine. But I figured, you know, I could check. We've got voltage coming in, we've also got a voltage regulator there and a bunch of resistors, but that's about it. And I thought if I could get the data sheet for the ESP32, I could perhaps probe it and see if signals are coming in or it's completely dead or stuff like that. I've also got currently like one dead Super Nintendo, one dead Mega Drive CD where other than saying, you know, continuity with a multimeter and making sure voltage going in, it looks okay. So what is failing along the way? And I thought I'll be using this to try and find out. Certainly not for everybody, and as I said, I can't speak with any authority whether it's any good or not. It's cheap and it seems to work. I mean, I'm slightly disappointed I can't do stuff like make it trigger on pulse width, which would be really good for looking at the sort of signals I want to look at in RC, but you know, that's an expensive one. The other reason about talking about something like this and saying, hey, I don't know anything, is quite often you good people out there who are experts at this will write down below and say, you need to look at this guide or do this or try this. You're quite welcome to do so, as I'm trying to learn more about how things work like this. Anyway, this has been the DSO-TC3 from FNRSI, I think, and it was kindly provided for review by Banggood, so if you're interested, there'll be links down below and you can check it out in more detail. I would normally say I hope that review's been helpful. I'm not sure if it was helpful, other than the fact if you're like me and you don't know anything about it, then maybe this is a good place to learn, I guess. Anyway, I'll catch you in the next video. Bye for now.
Well, you've made it to the end of the video, so thanks once again for watching. If you like what you saw, then please consider subscribing, and if you really like what you saw, then be sure to check out the link to my blog for a variety of ways in which you can help support this channel.